This conference will now be recorded.
Welcome everyone to another OCP session. So today we have Nobuyasu. Uh, he will tell us about enabling picosecond level space-time synchronization. A little bit about Nobu. Nobu obtained his PhD in physics from University of California, San Diego, UCSD. It is postdoctoral research at HIPAS Observatory at Fairbanks, Alaska, and then at NIST Boulder, Colorado. He then joined the National Institute of Information and Communication Technology (NICT) at Tokyo, Japan, in 2008 as a researcher. After working on research on atomic clocks for about 6 years, he has been working on development of ultra-precise and yet handy wireless synchronization technologies using commercial wireless communication devices for 7 years. So we saw his work in OCP Global Symposium. It was pretty impressive. Like we had these two units, and then each one of them were giving the PPS output and watching on the oscilloscope. So I'm pretty excited to see more details. So with no further ado, Nobu, the floor is yours.
Okay, thanks Ahmad for the introduction. And so again, my name is Nobu, and I'm really grateful for Ahmad to give me the opportunity to talk here. And so I'm going to talk about enabling picosecond level of space-time synchronization. And 2 weeks ago, there was a talk about also talking about picosecond level, but it was on atomic clock side. And now I'm going to talk more about the synchronization part, or sort of adjusting the clock to the other clock. So a little bit of my background, and I graduated in Japan, and I went to UC San Diego for physics department, and I was doing plasma physics, experimental plasma physics there. And then after my graduation, I went to Fairbanks, Alaska to study the natural plasma. And then I went to NIST Boulder. Now I go back to the experimental plasma physics. And but this time the focus is more toward individual ions and manipulating them to do the quantum information type of experiment. And of course, NIST Boulder have atomic clocks as atomic clocks as well. So that I learned about atomic clocks, and then I started to sort of migrate toward the synchronization research area. And then I went back to NICT. First, I sort of worked on the neutral optical lattice atomic clock. Then I made the ion type of atomic clock. But then I'm now actually working on the wireless synchronization that I'm going to talk today. And right now I live in Sunnyvale, California. So NICT is Japanese government research lab, and focused on ICT. And one of our sort of mission is to deliver or make and disseminate the Japan Standard Time. And so our function is like a NIST Boulder time and frequency division. And and so again, I mean, we are making sort of clock for Japan, and clock have 3 components: oscillator and counter to count how many times the oscillator oscillated, and then put it into a clock time and put it display. And also we need to sort of adjust the clock time to time. And corresponding to those, we have atomic clock like cesium atomic fountain, and also we have strontium optical atomic clock, and we also have indium and calcium ion clock as well for the sort of oscillator. And we have the function to disseminate JST, and also we have the technology to compare with the UTC to make sure that we have the good track. And then our talk today focuses on this sort of technology implemented onto the communication wireless module. And so our vision is really to sort of summarize into the word space-time synchronization. And the time synchronization is obvious. We want to have remote things to share the same time. But the reason we added space is because when you synchronize time, you actually end up in measuring the spacing in between those devices as well, after all. So why not why not synchronize both time and position or coordinate? In other words, if the devices, when they communicate, they can share the time, and also they can know each other's position relative to sort of the base. So, I mean, we want to sort of develop this vision in order for the future that the things are not just connected, but they can collaborate. And in order for that, we believe they need to be synchronized. So our final goal that we vaguely envision is that the things and the information and people are moving around autonomously in 3D space. But in order for that to be achieved, we probably need to practice first in much rural area, like autonomous maintenance of the forest, for example. And for that to function, we first need to have the synchronization infrastructure being employed at the sub-nanosecond accuracy. And at the moment, we are trying to see if our technology can contribute to the cloud synchronization, or of course this OCP, TAP is the place that we would like to contribute. Now, the technology that we rely on is based on the technology called two-way satellite time and frequency transfer. This is when we compare our JST, Japan Standard Time, to the UTC. We need to compare with the clock in Germany. And so, I mean, one of the way is to use the satellite to transfer the time. But of course, Japan and Germany through the satellite is a long way to connect. So if we just send the clock signal to Germany, it will have a long transmission time added onto the clock difference. So that to compensate or to measure the propagation time, the comparison need to be in both ways. And also, we have been using this technology over 15 years, and we know it works well. And so our attitude was, well, if it's working that good, then why not we use the same protocol to the commercial wireless modules. Of course, it won't reach to Germany, but in the range of the wireless communication, I think we can do better than that using the satellite. And so bottom line is, I mean, we tried and it worked. So I'm going to talk about that. Our first proof of principle experiment, we used the combination of commercial transmitter, in this case 2.4 gigahertz Zigbee transmitter, and received the signal with the USRP software-defined radio, and we used the rubidium clock. And our goal is to measure the time difference between these two clocks. And again, by transmitting the signal in both ways, we can, from those data, we can subtract the clock difference phase and the phase associated with transmission delay. And we can separate them and plot them together, and this TD blue is for the propagation delay, and we can see that it doesn't change. And if you look at the standard deviation, it's 2.2 picosecond standard deviation. And if you look at the clock difference, you can trace the clock difference. And one thing to note here is that we are in this data, we are looking at the phase, not the time of arrival. And so that gives much higher resolution. But on the other hand, you need the data wraps at 2 pi, so you need to unwrap data in order to sort of trace back the clock difference. Anyway, we showed that the floor or noise floor of this measurement is 2.2 picosecond. We can say that we are also doing the clock measurement at the 2.2 picosecond level, and this is our first experiment and put into in this ICE journal. And then from there, we decided to make a module. And one thing that we are still proud of is that we didn't go for FPGA. We directly went to using the chip as a sort of receiver, RF chip as a receiver to sort of let the work of software-defined radio done by this RF chip. And this MPU serves as a PC, and this TCXO serves as a rubidium clock. And so by skipping the FPGA, it's much cheaper and can be smaller size, and also it consumes low power. And we saved a lot of time for development as well. And that credit all goes to Satoshi Yasuda, and he's the one who designed everything and who wrote the firmware in it. So he literally did everything to make these. And we made several versions. We made up to 6, version 6 is our current version. And the version 2 is with the 20 milliwatt power, its range is a couple of 100 meters. And this third version 3 is using 250 milliwatt, and you can reach 5 kilometers. And this is what we could do with Japanese regulation. But I know if it's in US, we can put up to 1 watt, so we can easily reach kilometers. And with the latest version 6, the clock accuracy is 35 nanosecond with 16 picosecond jitter. And we are not happy with this clock accuracy yet, so we are still working on it. And we are trying to get it smaller, and eventually we are hoping that it will reach order of tens of picosecond. Anyway, with this module, there are 2 things we can do, and one is to look at the clock difference with the phase. And if you have, we have 2 YY modules here, and each one of them have their own local clock or local oscillator, and the local oscillator's frequency is not exactly the same. So both modules make 10 megahertz out of this local oscillator and connect to the oscilloscope. And so they think they are both creating 10 megahertz, but in reality, the frequency isn't the same because of the slight difference of the local oscillator. But YY can measure this phase drift and feedback to the frequency. And now both frequencies are locked, and we call this a phase lock state. So this display is 10 megahertz, but it's actually at 920 megahertz. The carrier phases are synchronized. And the other sort of or sort of additional thing that we can get is the propagation delay time. And if you monitor the propagation time, delay time, and unwrap them, then you can see that as the module goes further away, the propagation time increases, and when it gets closer, propagation time goes low. So this is virtually a sort of distance measurement, or more precisely, distance variation measurement. And so, I mean, we tried to make use out of it. And one thing that we tried is we put one module on 60-meter iron tower, and the other one on top of the building, 120 meters away. And we monitor the distance. And since we can monitor it at millimeter accuracy, we noticed that every day toward the noon, the distance gets shortened by 2 centimeters and goes back after the sunset. And then next day, the sort of distance gets shortened by 2 centimeters and back. So there is a sort of periodic motion, and we first didn't believe it, so we compared with the laser range finder, and it was correct to the millimeter accuracy. And then so our interpretation of this motion is that when the sun goes out, the south side of the iron gets heated more than north side and expand more. In the end, the whole building tilts toward north by 2 centimeters. And Satoshi now expanded that to not just peer-to-peer, but made in this case, 7 modules mesh network. So these 7 modules sort of course, when it's not phase locked, the frequency of all the modules are same with the leader. So it goes right, some goes right, some goes left. But as you press the button, the RF signal sends out to phase lock. And so they all start to feedback to the local oscillator. And now the movie is still running, but they are all phase locked. And the interesting thing is when you have 7 modules, there are 21 combination of one-to-one comparison. And both clock difference and the propagation phase is monitored at all 21 nodes. So actually it has a lot of measurement in it, but if it's not moving, it's not that interesting. And so Satoshi made this setup to measure the two-dimensional position of this helmet by putting 2 modules on the helmet, and also 2 as a stationary. And we used we used the laser range finder to measure the position of this prism connected to the helmet. And this is used, at least in Japan, it's used at construction site, and they are supposed to measure at millimeter accuracy. Anyway, this gives the ground truth, or the answer. And so Satoshi wears the helmet, and 2 stationary modules are here, and on the left is with YY, and with the right is the laser range finder. And you can see that both measure the position in real time, and basically they measure the same thing. An interesting thing is actually there are 2 dots corresponding to 2 modules here, so you can see which direction Satoshi is aiming at as well. And well, more than half years ago, more than half year ago, I learned that there is this group, and so I'm fascinated to this group. And last month we attended the OCP Global Summit, and there we had conversation with Ahmad and Julian. And at the moment, I think it would be interesting if we squeeze this wire module into this U-blocks form factor, and this will give this card another sort of route to synchronize, not just the Ethernet route, but if you are physically close enough to reach with 920 megahertz communication, then you can synchronize them together. So you have this will give another sort of route to synchronize the time card. And we are hoping that we will make mock-up by probably the end of March or so, and then we want to try it out. And we also are working on sort of trying to make this space-time synchronization more global word. So we went to ITUR and successfully put the word wireless space-time synchronization into future technology trend for IMT 2030. And they are in these categories for the low latency communication and for the positioning. Again, we are aiming to sort of this type of things are moving around autonomously, but in order for that to be achieved, there are many more steps to be taken, and we are working on very first step. So in summary, this is the summary that we have demonstrated the feasibility and cost effectiveness of this space-time synchronization module. And the fact that we can make module makes the small and low cost and low energy consumption. And for the era of synchronization of things, it is crucial. And we are, as a first step, we are aiming to contribute to the data center timing solution. And we know that we cannot do this by ourselves, so we are seeking international collaborations. So that's it for my talk, and I'm happy to take your questions.
Thank you very much. So let's open the floor for some questions. But before we get to the questions, let me share something uh, like. Can you go back to the slide where you showed the form factor? Yeah, so we are actually trying to standardize this form factor. So this form factor, uBlocks, Trimble, Fruno, there are a bunch of other, hopefully I didn't forget names there. They're all making modules with this form factor, and it's been a standard without really being standardized. So what we're trying to do now is, let me see if I can share my screen. Yeah, sure, it doesn't matter. So basically, we have a proposal for the RCB form factor, where we want to have all the dimensions and everything set, but you can do whatever you want with your own board and so on. We've been thinking, like, let's say this technology Nobu is talking about, or let's say even like these Leo-based technologies can sit there, as well as the one that Wim was talking about, which you recover the clock from 5G, and the connector stays the same, like this 2x4, but we can have, let's say, an expansion, another 8 pins on the top. So this can be again reused for interoperability. So you just take this and swap it. And we want to do the same thing actually for the atomic clock, where we want to actually have this large form factor, kind of standardized, where you, like for example, if you're familiar with the one that microchip, the approach microchip takes, is like they have a little board-to-board connector right in the middle. Well, you can still do that, but again, we're not restricting anyone. It's more like a guideline. If you follow that, it makes things more interoperable and interchangeable. But if you want to just have, let's say, I mean, most of oscillators, if you see like out there, they have pretty much all the pins except 9 and 10. 9 and 10 are like newly coming in, are the basically a single-ended PPS in and PPS out. So if you're interested in collaborating on this, please send me an email and I will share that with you. Like we're basically just going through a chain of emails for either one of them, and then we will hopefully soon make it as a OCP contribution. So it just goes on the website, and this remains on the GitHub. And again, not written on stone. It can be always updated, upgraded, changed, whatever. It's open to any feedback. I just want to have this confusion basically between like, okay, which form factor we should use, what should we do, like what's the best thing. Like I want to have something that gives you maximum compatibility, but again, is not restricting anyone. Also, for the supply, I'm keeping it open. You can go to 3.3, 5, 12 volts, whatever works for you. And yeah, so let's get back to the question sessions. Unmute yourself if you have questions.
Hi, this is Ravi from Apsara Research. I have a question for you. Did you guys do any work on absolute distance measurement from the phase metering, or you only looked at relative?
I'm sorry, so I didn't hear that. So what did
So,
you ask?
so when you put the systems on the building and you measure a 1 millimeter variation over time, um, did you ever try to look at whether you could measure the actual distance using some sort of phase counting, or is that beyond what your system could do?
Okay, so well, we want in order to test that, one thing we did was to use the laser rangefinder. So we measured the relative distance, and it was, and I mean, it agreed with our measurement. And we also tried to do the GPS and try to get the absolute position change, but I mean, it wasn't. I mean, we couldn't get the enough resolution, and we could.
No, but the laser rangefinder would have given you an absolute distance as well, right?
Yeah. Okay. So,
So you,
uh, are you asking whether we did the distance measurement?
yes,
Okay. Okay. To answer that question, at the moment we are able to only measure the relative distance, but the absolute distance is suffers with the 35 nanosecond uh, offset in time comparison. So in that sense, the 35 nanosecond refers to about 10 meter. So at the moment, our distance measurement is as good as 10 meter. Does it make sense?
understand. Thank you very much.
Thank you. Thanks for the question.
I have a question, Nobu. So this is based on a carrier frequency, right?
That's right.
So can you have, let's say, multiple? So then, let's say you can have synchronization. I mean, boundary clock.
So I guess your question is more like, can you do chain connection? I mean,
Yes.
chain link. Okay.
Yes.
Yes, I think if we work on it, we can do it. But we didn't got time to ask. I mean, Satoshi is at the sort of not being able to work on it, but it should be technically possible.
Yeah. Any more question? Maybe you can like provoke some questions. Roll, do you think this somehow sits in your business with Atomic Run, let's say for validation?
So I mean, our attitude toward this, sorry, I mean, so if you hear the noise, I'm sorry for that. But now the attitude, I mean, in combination with atomic clocks, is that it's really, if you think of the good synchronization, it's sort of balance between good stable oscillator and the frequency and the accuracy of the comparison.
Yeah.
So our technology it gives the sort of handy method to compare the clock at picosecond level.
Yes.
And how often do we need to compare really depends on the stability of the oscillator and also the accuracy that you want to be in. So if you have very good oscillator, then you don't need to you only need to compare like every like a minute or so. But at the moment we are comparing like 20 times a second, which is actually way more frequent than just doing the phase lock. But we do measure 20 times because some people want to use it for the position variation measurement.
Yeah.
So all those sort of parameters will be optimized for the application. So depending on the application, I mean, we can do sort of stretch one parameter and so on.
Ian, go ahead.
Um, sorry, you mentioned that there would be a commercially available unit. Do you have a timescale on when your vendor will be providing samples of these for
Okay,
purchase?
yeah. Thanks for that question. So I'm trying to work on we are trying to collaborate with Japanese vendor that but due to the sort of limited supply of the integrated circuits and so on, it will take some time to actually make the first version available. It will be order of 1 year or so at the moment, seems like. And I'm sorry about that.
Ian, go ahead. You have a question? There's some audio issues. So maybe until Ian gets back. So Nobu, have you tested this in comparison to, let's say, UWB, and how does it stand?
Oh, I see. We never really compared with the UWB. So what we have done is the compare with the laser range. I mean, if it's distance oriented, it's laser range finder, and also if it's time related, we just use the wire. I mean, the coax cable. We use long coax cable to check the timing of it. So, I mean, direct answer to you. I mean, we didn't really collaborated or tested against UWB. Is the sort of simple answer.
And maybe like a follow up on that, how would this, let's say, coexist with Wi-Fi if we want to have, let's say moving forward? I mean, Wi-Fi itself tries to get to high precision, but I mean, let's say if it reaches to the point that you want to have something coexisting, how do you see this coming
I
together?
see. Yeah, I think actually I mean, we already demonstrated that it works at 2.4 gigahertz, even though it was Zigbee. And so the modulation is different. But I think, I mean, the reason we chose 920 megahertz is that because there was one Japanese chip maker who was available, who was at the moment developing new chip. So we could ask them to register some numbers, I mean, some
I see.
measurement in
I
the
see.
chip. So even the problem with Wi-Fi is the Wi-Fi chip is very, I mean, it's all set and nobody is really making new one. So
Yes.
there is not much room to sort of add some feature. And so if you check carefully, chipset might be able to do the things that we want to do already, but we haven't sort of collaborated with the Wi-Fi chip makers. So there is a chance that we can do it with Wi-Fi as well. But on the other hand, it might cost a lot to remake the Wi-Fi chip in order to do this Wi-Fi.
And then the range is like, I mean, you showed in the video like an outdoor, like what's the maximum range you got?
Yeah, so far, I mean, we have checked that with 5 kilometers, we can do it.
That's
And so
more than what you need for a house.
and
Sorry, go ahead. Sorry.
no, and that is with 250 milliwatts, and in US we can put even more power to it. So
And these are just like, you can, it depend on the frequency, right? You don't need to have it always running, right? The 250 milliwatt, or you need.
no, I mean, you just transmit only when you want to compare.
Yes. So there is a question. I mean, Ian, I don't know, Ian, you want to give it last try your microphone? I guess we have problems with the microphone. Okay, so this is a question from Ian. Ian was wondering what the steps would be to get this into more hands and on trajectory to become operational in wider hands outside the lab.
So yeah, I mean, we made our prototype modules, but we have been for last 4 years we have been trying to make it commercialized so that it can be sort of used by more people, and that we are trying to. I mean, we are still working on it, and looks like there may be one vendor that is willing to who is willing to commercialize this module. So that definitely helps. I mean, that what helps. And also with the module that we created by ourselves, we are collaborating with universities. And so far, we have collaborated with the universities in Japan. Like some people are using it for the communication to demonstrate the sort of lower latency communication. Another person is doing for the more channel, so the SSCDMA being optimized by sort of synchronizing the reception time. And also we collaborate with the Tohoku University. They are working on robots, and they use that for the both communication, I mean, improvement of communication, and also improvement of the localization of the robots. So, I mean, with those sort of studies, I think we can realize more application, and hopefully some of the application will be able to, well, to sort of make a business and or contribute to the business, and then I think it will expand. But sorry, I mean, at the moment, bottleneck is how to distribute this module is at the moment is sort of at the bottleneck.
Yeah, I wish I had some of our RF colleagues here, but I can assume some of the questions they will ask. Let's see if there's more questions. If not, I will start with some RF questions. Any more questions? Okay, so let's start with the RF questions then. So in terms of bandwidth, like what's the bandwidth you get? Like, and let's clarify again, what was the carrier frequency for this?
Okay, so the one we made is the carrier frequency is 920 megahertz, and in Japan, the way they use 920 megahertz is a sort of narrow band. So we modulate at only 100 kilohertz or so.
It's double-sided, right? Also, right?
Mm.
Okay.
Yeah, and so anyway, so it's at the moment it's narrow band 920 megahertz, but as
I'm
long
not
as we can.
that familiar with 900. Like, are there like things environmental or something, like in terms of absorption? Do you get let's say different ranges and different, like, I don't know, weather conditions and so on. And then also, what about the reflection? Do you have problems with reflection depending on the environment? Again, whatever we had, like, what was the status of the study on
Yeah. So if
these?
you compare with 2.4 gigahertz, it's lower frequency. So it's, I mean, it can go around, or it can reflect, and in the end, I mean, it reaches further is usually what you see. Now, if you want to synchronize, and since you are measuring both ways, so whether you reach by bounce off or whether you reach by going around, it doesn't really matter, because the path that the signal takes for the one way and the other way are the same after all. So you can still measure, I mean, compare the clock accurately. And in that regard, if you want to use in long distance, I think lower frequency tends to be better. Now, of course, if you go to higher frequency, the period is going to be less. So suppose we have the same phase measurement signal to noise ratio, then by going higher frequency, your measurement, the clock measurement gets more accurate in a sense. But on the other hand, you need to be careful that your sort of cycle slip is much sort of high. I mean, the cycle is shorter, so in order to track how many cycles it's actually proceeded, I mean, you need to be careful. I mean, and in the end, we found that around 1 gigahertz, I mean, 920 megahertz is actually was a good place to start in this application.
So, in terms of like the how you do the whole measurement, the method is T1, T2, T3, T4. So you basically have you look for offset and delay. So that doesn't that tell you? I mean, you have the delay. I mean, you correct for the offset, but you have the delay, so that can tell you the distance. Isn't that the case? Like, because someone was asking about the distance.
Okay, yeah. So I didn't make it clear in my talk, but we are measuring two things. One is the phase measurement, and the other is the time measurement. And so with the phase measurement, you can
Oh,
measure the phase accurately, but you don't know the absolute time difference, or
yes,
you don't know the absolute distance.
yes.
In order to measure absolute time or distance, you need to know the time. You need to be able to do the time measurement well. But since the time scale for the time measurement is much worse than the phase measurement, it's by factor of 10,000. So it's much less accurate. And so even though when two modules are phase locked, the time doesn't wander off anymore. But depending on your time measurement accuracy, the sort of error for your initial time measurement stays as a offset between two clocks. So the 35 nanosecond I was referring to in my talk refers to the sort of time. I mean, it comes from the time measurement not being accurate enough, and we are working on it. So uh, yes, I mean, 35 nanosecond is corresponding to 10 meter, I think.
This is
So
very similar to White Rabbit. So then I see, like, it's very interesting. It's like on the phase. It's not like on the times. It's like
that's right,
it's more a
So
wireless White Rabbit than wireless PTP. You know? RJ, you want to ask a
Could
question?
I have,
Yes, go ahead.
sorry, could I clarify one thing?
Yes.
About the distance. When you say that, um, so what if the observer moved more than one wavelength between measurements? How would you handle that? Because if you don't, do you know exactly number of cycles that happen? Because if you don't have good timing, then I guess you're accurate to 1 millimeter within one wavelength. Is that correct?
That's right. Yeah. So yeah, Ravi, you have very good point that suppose we have 900 megahertz and 2.4 gigahertz and maybe 400 megahertz or so. If we have multiple wavelength, it's like improving GPS as well. That by using the multi wavelength, and even though you may not know the ambiguity of the how many cycles, but then you can still get much better measurement in terms of the distance or time. So there are things that you can do with using several wavelengths. I agree.
So there is a question from Daniel, and he's asking, what's the time accuracy when the receivers are moving, and how do you deal with the asymmetry of the link?
Okay, that's a very good question. So at the moment with our module, we are using single band, single channel. That means we need to uh, time. I mean, we time duplex the one way and the other. So whatever the environmental change between time, the time that that one signal goes, and the difference with the time the second signal goes out will be sort of reflected to the time measurement. So, and at the moment, so it depends on how sort of closely both signals are going back and forth, but it will suffer if you move quickly. I agree. So at the moment, we are starting with the sort of more stationary applications, like if you want to use like time synchronization is one thing, or like the small variation of the really slowly moving thing, like the position of the iron tower is one thing. Like the kind of infrastructures, slow change is something that this module can is good at measuring.
So the asymmetry, basically, I mean, you assume symmetry. You assume because you're using the same channel, you assume on the media the same thing. I see. And then also in the charts, like you were showing, like I mean, what is special about this is, I mean, you have the same radio taking from the TX and the RX at the same time with two channels. Is that correct?
Oh,
That's you assure that you get the best precision on the TX and RX. Is that correct?
that's right. So actually, with the first experiment that we did, we were actually using two channels on one way and the other. So if we use that strategy, I mean, we can sort of synchronize the transmission and reception at the same time, and then we don't need to suffer the asymmetry.
Yes. Yes. Okay. Any other questions? Let's see. A lot. Anything you want to share with the group before we call this meeting?
I'm just glad that this one is recorded. We unfortunately don't have a good recording from your previous presentation, just
No,
the slide. So,
that one is available. That's just
yep,
we're processing it here.
correct. So I'm very glad. Thank you. Thanks for
Yeah.
sharing, and happy Thanksgiving to everyone.
Thanksgiving.
Yeah. Happy Thanksgiving to
And
everyone. Okay. So if no more questions, we'll give you back 8 minutes. Does that sound good?
Okay.
Great.
amazing.
Great.
Ahmad, I have one question about the form factor.
Yes.
That
Yes.
I saw, I mean, your version of the defining the form factor is much better than what we can see with uBlock's website. So, I mean, I'm very much want to get
I
the.
mean, uBlock's I forgot his name. So he basically helped us a lot with details, like how we should basically describe it and so on. And I look forward. I look forward for everyone in the community to add more details to this. So please send me an email if you're interested. I'll just CC you back into the whole chain, and then we hopefully, let's say in 2 3 weeks or something. Maybe again, a lot is here. A lot. If we want to submit contributions, when would be realistic? Like maybe for January, right?
Yeah, we'll probably hit the January train.
Yeah,
I would,
January. Yeah.
yeah, I would encourage you to reach out to me and Ahmad on that, and we'll start processing the
Yeah.
necessity in order to submit.
So then the cutoff will be like it's I'll say middle December or something, right? Right. So
Yeah,
to
that sounds
okay.
right.
So let's do this. Let's say let's have a cutoff time for this in 2 weeks. So let's say first week of December, and when once we don't see like any more comments or something, everything is converging, then we'll submit it. Again, it's not written on stone. Then it can go through revisions. But right now, just the first version. Let's have as much as possible comments and details from agreements from everyone. It was similar to what we have, let's say, with a profile and so on. Okay.
Just a
Correct.
note
Yeah.
on that, Armando uploaded RCB F9T that's compatible with the time card, so the same form factor, onto the time card GitHub. So if you're looking for a reference design that you can look at the mechanicals and the layout and everything, that's on the GitHub already.
Wonderful.
Is
Okay.
the guy from uBlock Samuli? Are you talking about Samuli?
Samuli, yeah, sorry. Thank you
Yeah.
for reminding me. Yeah, yeah. So Samuli contributed a lot on where we should start. Then, I mean, we did a lot of this back and forth in person in ITSF because we had everyone was there pretty much. And but this is like again more formalized. This document, we just go through it. Any more things we want to add? What we consider like specific? It's not probably a good place to put it there. It's more for what is generic. And then once we have everything, so we're calling it also an RCB, standing for Receiver Carrier Board.
Awesome. Can you send so everybody interested in going and seeing what the current contribution is, and to see if you want to instead of
I will
us
send,
broadcasting it, please reach
yeah,
out
I
to
will
us so
send it
we'll have
actually
it
to
forward.
the mailing list.
Yes.
Just like I'll say today or tomorrow, I'll have it sent to the mailing list. And then please feel free, everyone, just keep updating it and so on until we converge.
Thank you, Alan.
Okay, great. Hearing none, let's finish the recording.